Hi guys, in pursuit of technical knowledge and just to gear up for the new engineering entrants, myself, Pranav is here to deliver today's presentation, Power Transformer Part 9. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with dielectric loss. Transformer dielectric of or insulating materials must possess very low conductivity in contrast to conducting materials so as to insulate reliably the conducting parts from one another and from earth structural components. However, the performance of the dielectrics is characterized by the volume resistivity and surface resistivity. The volume resistivity is expressed in ohm centimeter and the surface resistivity is expressed in ohms. Again, I repeat, the volume resistivity is expressed in ohm centimeter and the surface resistivity is expressed in ohms. Dielectric material having higher the volume resistivity and surface resistivity indicates the higher its quality. The resistance of the dielectric material is directly influenced by some external factors, such as temperature, humidity, and surface contamination. Rise of temperature as well as high humidity would have to instigate sharp reduction of insulation resistance and in turn increase the leakage current. While the dielectric material is subjected to a time-varying electric field, which produced due to an alternating voltage as applied to it, then some fraction of the electrical energy has to absorb by the dielectric. The electric energy as absorbed is thereby transformed into heat in the dielectric. This loss of energy is designated as dielectric loss. Dielectric losses take place in the insulating materials such as transformer oil and the solid insulation of high voltage transformers due to have large electric stress. The optimal dielectric properties of insulation systems is one of the most basic requirement for safe operation of power transformers. Due to prolonged operation, the transformer oil is subject to change its parameters such as dielectric strength, dielectric dissipation factor tan delta, moisture content, chemical parameters, that is dissolved impurities, dissolution of copper, and physical parameters, etc., etc. Dielectric properties of mineral oil as used in transformer has constantly been suffered from electrical and mechanical stresses while a transformer is in operation. While at high operating temperature, the oil would have been contaminated due to have chemical interactions with winding materials and other solid insulations. That has instigated gradual change in original chemical properties of transformer oil as recommended for, and over time, it has lost its intended purpose. Transformer's efficiency will be directly affected with the oil in the transformer gets deteriorated. Transformer insulation once contains a high content of moisture which causes high dielectric losses. In an ideal perspective, all dielectrics are insulating materials. All dielectrics or insulating materials are considered as perfect capacitors with lossless phenomenon. Again, I repeat, in an ideal perspective, all dielectrics or insulating materials are considered as perfect capacitors with lossless phenomenon. Long-term high voltage operation of a power transformer will cause aging, which may have to instigate various dielectric losses in its insulation system. Moreover, various types of electrical, mechanical, and thermal stresses are extensively developed, which may accelerate different chemical processes, influence the chemical composition, and gradually degrade the overall dielectric properties of the insulating material. Dielectric losses are determined by the expression PD equals to V square omega tan delta C, where V is the voltage, omega is the angular frequency, radian per second. Omega is equal to twice pi f, where f is the frequency of the applied voltage. Tan delta is the dielectric dissipation factor. C is capacitance of the dielectric. To ascertain the basic electrical properties as well as eventual condition of power transformer insulation system, the dielectric losses have to be evaluated on a routine basis by the process of determining the dielectric dissipation factor and capacitance of the insulation system. In order to fulfill this diagnosing task, a variety of different types of dielectric diagnostic measurement techniques have been developed. It is therefore recommended to conduct testing periodically at site to assess the effective dryness of the insulation system of transformers. Electric field strength of a dielectric. The electric field strength in a dielectric is inversely proportional to the permittivity of a dielectric. Again, the permittivity of a dielectric should have to depend on temperature, that is 20 degrees centigrade, and frequency of the applied voltage, that is 50 hertz. While selecting dielectric materials which are to operate in series, it is to be adjusted to have their permittivity as close as possible to each other. This has ensured an uniform distribution of the electric field within the composite insulation network, and thus in totality would have to enhance the electric strength. Any sort of dissimilarity for choosing of their permittivity and thickness of the insulation components, the electric field strength may have to exceed the electric strength of the insulation, and it will ultimately fail. Electric strength of dielectric material. The property of dielectric material which has to make enable for withstanding high voltages as desired without any breakdown would have to be expressed in terms of the minimum electric field strength or electric stress, of which will cause breakdown of the dielectric, that is in terms of breakdown voltage per unit thickness of the dielectric. That is EBS equals to VBV divided by T, where EBS is the breakdown stress in kilovolt per millimeter, VBV is the breakdown voltage in kV, T is the thickness of the dielectric in millimeter. Hence, the breakdown stress of a dielectric material is therefore be referred as the electric strength of a material or dielectric strength of the material. Dielectric strength is one of the most basic criteria for the selection of the insulating components of any electrical equipment. Insulating materials used in transformers. To have a long span of reliable operating characteristics, the insulating material as used in transformers should possess the primary thing to resist electrical stresses. But other than electrical properties, the insulating materials would have to possess some additional properties so as to have an ability to withstand other stresses which the insulation encounters during manufacturing process, storage, and operational abnormality for prolonged periods. Additional properties are as follows. A, thermal stability to withstand elevated temperatures, mechanical strength to absorb abnormal mechanical forces, elasticity and flexibility, oil resistance, moisture resistance, and last of all, chemical resistance. Transformer operating temperature would have been the prime parameter for maintaining the best possible thermal stability of its insulation components. It is as because that higher the transformer operating temperature, the higher will be the rate of its chemical degradation of the insulating components. And hence, the lower will be its operating life. Insulation system is classified with its maximum allowable temperature. Electrical equipment can have to be downsized by implementing an insulation technique of higher thermal endurance. In early days, the insulation materials as classified with temperature class were simply categorized into materials of natural, organic, inorganic, and combination thereof. In the late 1930s, the types of synthetic resins were introduced in the insulation technique of higher thermal endurance. In the late 1940s, the silicon resin would have become a well-listed insulating item featuring excellent thermal endurance up to 180 degrees centigrade, H-class insulator. In 1977, the Japanese Industrial Standards Committee had drawn up JIS C 4003 classes of electrical insulation and their maximum allowable temperatures. Insulation class, maximum permissible temperature. As per JIS C 4003 1977, insulating materials to have the respective thermal stability. Insulation class Y, permissible temperature, maximum permissible temperature 90 degrees centigrade. Typically made of cotton, silk or paper, natural rubber, polyvinyl chloride, etc. Class A, 105 degrees centigrade, maximum permissible temperature. Reinforced class Y materials with impregnated varnish or dielectric liquid such as insulating oil. Class E, 120 degrees centigrade, maximum permissible temperature. Insulators used for enameling of wires, as for example, PVC. Class B, 130 degrees centigrade, maximum permissible temperature. Inorganic materials or combination of materials such as mica, glass fiber, asbestos, etc. with suitable bonding, impregnating or coating substances. F-type insulation, that is 155 degree centigrade maximum permissible temperature, making up gradation of class B materials with adhesive silicone and alkali resin varnish of higher thermal endurances. Class H, 180 degrees centigrade, made of inorganic material as for example glass fiber, mica products with or without support materials, rubber, glass cloth, etc. glued with silicone resin or equivalent adhesives. C, which is greater than 180 degrees centigrade, made of 100% inorganic material such as mica, ceramic, glass, quartz, etc., glued with silicone resin of excellent thermal endurance, maximum permissible temperature 225 degrees centigrade, polytetra fluoroethylene resin, maximum permissible temperature 250 degrees centigrade. On 1st September 1926, the National Electrical Manufacturers Association, which is called NEMA, was formed to improve the state of electrical manufacturing in the United States. Since then, it has to represent as the largest trade association of electrical equipment manufacturers in the United States and defined specific standards for various grades of electrical components typically used in industrial application. As per NEMA, insulation class is represented through the maximum temperature rating that can be withstood by the transformer insulation for dry type. NEMA insulation class, 105 degree, that is A, NEMA letter designation, NEMA insulation class, NEMA letter designation, ambient temperature, maximum allowable temperature rise, maximum allowable operating temperature. NEMA insulation class 105 means NEMA letter designation A, ambient temperature is constant in all the classes, that is 40 degrees centigrade. Maximum allowable temperature rise, centigrade 50 degrees centigrade and Fahrenheit 120 degree Fahrenheit, 22 degree Fahrenheit. Maximum allowable operating temperature 105 degrees centigrade in Fahrenheit 221. 130 insulation class NEMA insulation class. NEMA later designated as B. Ambient temperature 40 degrees centigrade. Maximum allowable temperature rise 80 degrees centigrade or 176 degree Fahrenheit. Maximum allowable operating temperature 130 degree centigrade, 266 degree Fahrenheit. Insulation class 155. F designation. Ambient temperature 40 degrees centigrade. Maximum allowable temperature 105 degrees centigrade, 221 degree Fahrenheit. Maximum allowable operating temperature 155 degrees centigrade, 311 degree Fahrenheit. NEMA insulation class 180. NEMA later designation H. Ambient temperature 40 degrees centigrade. Maximum allowable temperature rise 125, 257 degree Fahrenheit. Maximum allowable operating temperature 180 degrees centigrade and 356 degree Fahrenheit. Insulation class 220. NEMA later designation R. Ambient temperature 40 degrees centigrade. Maximum allowable temperature rise 150 degrees centigrade, 302 degree Fahrenheit. Maximum allowable operating temperature 220 degrees centigrade, 428 degree Fahrenheit. Note: transformer with class 220 would have to be designed with the insulation system whose maximum temperature rise is always be kept lower than the standard 150 degrees centigrade. No restriction has been imposed in designing transformer with same insulation class 220 having maximum temperature rise of either 125 or 80 degrees centigrade rise. Transformer of insulation class 180 can also be allowed to design with maximum temperature rise of 80 degrees centigrade. Insulation class 155 and 105 transformers are not typically designed for other than their standard temperature rise, that is 105 degrees centigrade and 50 degrees centigrade. Maximum operating temperature equals to ambient temperature plus maximum temperature rise plus 10 degrees centigrade hotspot allowance. Maximum operating temperature equals to ambient temperature, that is 40 degrees centigrade, plus maximum temperature rise plus 10 degrees centigrade hotspot allowance. Life of the insulating material gets halved with every 10 degrees centigrade rise above its specified class of temperature. Insulation class of transformer oil. The mineral oil with which the transformer is to be filled must have to be maintained the pertinent standards, as because the oil is used for transformer cooling and for providing necessary insulation between winding and the tank of the transformer. Mineral oil would have to sustain temperature rise up to its flash point 140 degrees centigrade. But technically, the transformer is therefore supposed to be operated safely up to the temperature of the lowest safe operating temperature of any part of the transformer inside the tank. The most sensitive part of the transformer inside the tank is the winding and its insulation. The insulation of the winding is made of the press wood and impregnated paper insulation. The maximum allowable temperature for impregnated paper insulation is 105 degrees centigrade. Press board is made from unbleached sulfate pulp, and in combination with mineral oil, it is served as main insulating material in high voltage transformers. According to thermal stability, the press board is of insulation class A. The dielectric strength of the press board would have to depend on thickness and the medium where it is intended to place. Dielectric strength of the press board may have the ranges from 7 to 15 kV per millimeter in air and from 30 to 55 kV per millimeter in mineral oil of temperature 90 degrees centigrade. Press board is rather intended for immersion in mineral oil at up to 105 degrees centigrade and has enlisted with high mechanical strength, low shrinkage value, and good ability to resist creeping discharges. Therefore, transformer can be safely operated if the temperature rise of the winding is up to 105 degrees centigrade and not up to the flash point of the mineral oil, that is 140 degrees centigrade. Thus, the insulation class of oil filled transformer is considered to be of class A, and the maximum temperature of winding must not exceed above 105 degrees centigrade. Assigned temperature limit. No load and load losses both are converted into heat, which has to increase the temperature of transformer, active parts, that is core and windings, structural parts, that is clamps, tank, cover, etc., as well as of transformer oil. However, temperature rises of all components are supposed to be limited by the appropriate standards. While designing allowable temperature limits are to be finalized in corresponds to voltage rating, capacity, and type of cooling, including specific insulation and packing arrangements for mounting the windings of the intended transformer. 1. Reference ambient temperatures are taken as follows. A, maximum 40 degrees centigrade. B, for daily average 30 degrees centigrade. C, for yearly average 20 degrees centigrade. D, for water cooled unit, ambient is considered that of cooling water temperature. Number 2, oil temperature 100 or 105 degrees centigrade. Winding temperature. Number 3, A, average winding temperature for normal paper 85 degrees centigrade. Average winding temperature for thermally upgraded paper 95 degrees centigrade. Average winding temperature for Nomex 125 to 145 degrees centigrade. hotspot winding temperature. For normal paper, based on daily average ambient 30 degrees centigrade, 95 degrees centigrade. For thermally upgraded paper based on daily average ambient 30 degrees centigrade is up to 110 degrees centigrade. Number C, maximum allowed hotspot winding temperature for normal paper based on maximum ambient 40 degrees centigrade is 105 degrees centigrade. Maximum allowed hotspot winding temperature for thermally upgraded paper based on maximum ambient 40 degrees centigrade is 120 degrees centigrade. During short circuit, maximum allowed hotspot temperature for very short time is 250 degrees centigrade. Temperature limit for metal parts. Set value of temperature limit of metal parts in contact with winding insulation is as same as for temperature limit of winding. B, set value for temperature limit of other metal parts 140 degrees centigrade. Overload capability of a transformer is rather to be restricted by the prescribed oil temperature and hotspot temperature. And that is the reason these two are very important. Probability of paper insulation failure has become much more evident when the tensile strength of the paper is reduced by 80%. Insulation integrity of the paper can be assessed through degree of polymerization. When hotspot temperature exceeds 120 degrees centigrade, then there will be a chance of rapid deterioration of physical properties of the thermally upgraded paper. Rate of loss of life is doubled for every 8 degrees centigrade over 120 degrees centigrade. For every rise of 8 degrees centigrade over 120 degrees centigrade, the rate of loss of life of the thermally upgraded paper is doubled. Transformer efficiency. Transformer operates on the basic criteria of magnetic phenomenon. Though the transformer in general is highly efficient, but some of its energy is just dissipated as loss through its winding resistance known as load loss, plus the loss due to magnetic effects on the core itself known as iron loss. While transformer is at low loads, as for example under 30% loading, core losses will be the dominating factor. But with the increase of load, winding losses would have become much more dominant, and during full load operation, winding losses might be around 50 to 90% of the total transformer losses. Again, I repeat, while transformer is at low loads, that is under 30% loading, core losses will be the dominating factor. But with the increase of load, winding losses would have become much more dominant. And during full load operation, winding losses might be around 50 to 90% of the total transformer losses. Whenever transformer is energized, the core losses will then start instigating and remain constant all through, irrespective of load. Large power transformers may have the efficiency as high as 99.75%. And for small transformers, such as plug-in type used in electronic devices, maybe of the efficiency less than 85%. The technology and application reliability of transformer can easily be suffixed by the basic performance of its core and winding, as because both are essential source components for energy loss. This is the reason for which a bulk percentage of manufacturing cost of a power transformer will, however, be occupied by the process engineering of making core and windings. The transformer losses are thereby instigated from one, winding resistance, that is, flow of current through windings would have to produce resistive heating of the conductors. Number two, eddy currents, that is, induced currents circulate in the core may cause resistive heating. Number three, stray losses. Magnetic field as produced by the primary is not fully intercepted by the secondary, and some portion of the leakage flux may induce eddy currents within nearby conductive transformer structural parts, causing abnormal heat. Number four, hysteresis losses. Each time when the magnetic field is reversed, a small amount of energy is lost to hysteresis in the magnetic core. The level of hysteresis is affected by the core material. Number five, mechanical losses. The alternating magnetic field causes fluctuating electromagnetic forces between the coils and wire, the core and its adjacent metalwork, causing abnormal vibrations and noise which consume power. The vibration of transformers is a result of stray fields and has to affect the power equipment's normal operation, service life and reliability. The transformer vibration has two main constituents. A, winding vibration, that is being caused by the electromagnetic force generated by the interaction of the current in a winding with leakage flux, and iron core vibration, that is being caused by the magnetorestriction forces in the silicon steel sheet. A significant correlation has been exhibited between the problems of vibration and noise in the iron core of power transformers. However, vibration is mainly based on magnetostriction of grain-oriented silicon steel sheet. Under no load condition, as there is no current in the winding, so any sort of transformer vibration is therefore mainly generated by the core itself. The process cycle of magnetoresistance would have to instigate a vibration syndrome within the magnetic core of a power transformer. Such vibration syndrome may have an effect to create delaminating of magnetic core layers, and that leads to have some vibration with higher amplitude on the surface area of transformer tank. In power transformers, at the time of operation, several defects that can also be originated from this type of syndrome. Categorization of the defects. One, electrical defects. As for example, internal short circuits between individual winding turns, localized partial discharges, thermal defects, as for example, degradation of transformer winding, solid insulation, hotspots in transformer windings, mechanical defects such as loosening and displacement of windings, delaminating of magnetic core layers, magnetostriction effect is the cause of mechanical movement within the ferromagnetic core element of the power transformer due to the flux as propagated through the ferromagnetic core, while the core is subjected to have a constant changing of magnetic field, that is alternating magnetic field or time varying magnetic field, right? Though the intensity of physical expansion and contraction of the core elements is not so much significant, but because of constant movement of the core laminations may lead to have losses due to frictional heating in susceptible ferromagnetic core. Such occurrence has forced the magnetic core laminations to change their shape, and to limit vibrations would have been the resultant effect. This mechanical movement of the ferromagnetic core element is periodical in nature and is proportional to the primary voltage frequency, since the generated magnetic field has also periodically changing its value and is induced by the primary voltage. Therefore, magnetic core has to exhibit vibrations which are then transmitted to the surface of the tank through other structural parts of the power transformer. Again, I repeat, this mechanical movement of the ferromagnetic core element is periodical in nature and is proportional to the primary voltage frequency, since the generated magnetic field has also periodically changing its value and is induced by the primary voltage. Therefore, magnetic core has to exhibit vibrations which are then transmitted to the surface of the tank through other structural parts of the power transformer. As the vibration distribution path does have to emanate through multiple components, so the process of propagation has become a bit complicated. Humming noise has also to be evolved as an additional consequence of the magnetostriction effect. Due to have magnetostriction effect, the level of vibrations as generated from the magnetic core may sometimes overlap the vibrations caused by the windings due to electrodynamic forces. In that case, there would have been a different proposition to diagnose or detect any sort of mechanical defects within the transformer. By using best available resources would have been applied with proper coordination of technological evolution and measures to restrict these problems. Selecting the core material with thin laminated sheet of high-grade grain-oriented silicon steel having high magnetic flux density would have to contribute low no-load loss. Application of proper sequence of code stacking procedure may also have to facilitate for stabilizing the performance quality of the core. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.